Saturn's hexagon refers to a hexagonal ring-shaped cloud layer located at the north pole of Saturn, approximately in the region of 78 degrees north latitude of Saturn. The outermost hexagon has a side length of approximately 14,500 kilometers, 9,000 miles, which is approximately 2,000 kilometers, 1,200 miles, longer than the diameter of the Earth, and can reach a diameter of 29,000 kilometers, 18,000 miles, and may be as high as 300 kilometers in height. There may be jets with wind speeds up to 320 kilometers per hour, 200 miles per hour. The rotation period of this hexagonal structure is 10 hours, 39 minutes and 24 seconds, which is the same as the radio transmission period inside Saturn. This hexagonal structure, like other visible clouds in Saturn's atmosphere, does not move in longitude. The Saturn hexagon was first discovered during the Voyager mission. Later, when the Cassini-Huygens arrived at Saturn in 2006, the Saturn hexagon was also observed. During the Cassini mission, the color of Saturn's hexagon changed from blue to golden yellow. In particular, this hexagonal cloud structure only appears at the north pole of Saturn. According to the image of Saturn's south pole taken by the Hubble Space Telescope, there are indeed obvious jets, but there are no strong polar vortices and no hexagonal standing waves. The cause of Saturn's hexagon is still under speculation. It may be some form of standing wave, or it may be a new type of aurora. At present, some experiments have reproduced similar polygonal vortices, but it is uncertain whether it is related to the formation of Saturn's hexagons. Saturn's polar hexagon was discovered by the Voyager mission in 1981. The first thing that was noticed in the Voyager 1 image was a long-term hexagonal vortex around 78 degrees and around the North Pole. In 2006, the Cassini mission also observed the Saturn hexagon. Since Saturn's hexagon had not entered the Sun's range before January 2009, Cassini could only take thermal infrared images of Saturn's hexagon. Cassini can also move at the same speed as Saturn, while filming the weather pattern of Saturn's hexagon, so it can record the motion of Saturn's hexagon. After the discovery of the Saturn hexagon, many amateur astronomers tried to obtain images of the Saturn hexagon from the Earth when the Saturn hexagon entered the range of sunlight. Saturn's polar hexagon was discovered by the Voyager mission in 1981. The first thing that was noticed in the Voyager 1 image was a long-term hexagonal vortex around 78 degrees and around the North Pole. In 2006, the Cassini mission also observed the Saturn hexagon. The cause of Saturn's hexagon is still under speculation. Most astronomers believe that it is some form of standing waves in the atmosphere, but the hexagon may be a new type of aurora. One hypothesis put forward by researchers at the University of Oxford is that hexagons are formed where Saturn's atmospheric wind speed has a steep latitude gradient. At present, the polygonal structure has been simulated in the fluid rotating barrel in the laboratory. This phenomenon may occur when a circular liquid tank rotates at different speeds at its center and periphery. Its shape ranges from triangles to octagons, and they are formed between two different fluids that rotate at different speeds. Turbulent area. Other researchers said that the vortex escaping, a series of vortices, was observed in the experiment, but it was not observed in the hexagon of Saturn. The simulation shows that some shallower, slower, locally entangled jets that are in the same direction as Saturn's prevailing clouds produce boundary stability that coincides with the observed Saturn hexagons. The long-lived structure of Saturn's North Pole hexagon orbiting jet, plus the positive pressure instability of the North Pole vortex, NPV, system is similar to the observed hexagon. However, in many literature studies, pure jet airflow systems cannot produce such a phenomenon, so the power of the Arctic vortex, NPV, may play an important role in stabilizing the hexagonal jet. It has been suggested that wet convection may be one of the factors in the origin of Saturn's Arctic vortex system. A 2017 paper used a positive pressure rotating shallow water model to investigate the impact of wet convection, but believed that the importance of the Arctic vortex would not be changed.